Good morning, all of you. Today we'll continue class 12, solid state. So in the previous class, we discussed about properties of solids and electrical properties of solids, magnetic properties of solids, defects in solids, and the structures of solids. So all those are theoretical part. And now we will come to the numerical part of this chapter. Very, very important topic. That's why I have kept this at the last. And in the previous topic, we discussed about all the properties of solids. Now we are going to discuss about how to find density of a solid. So density of unit cell. So density of unit cell is equal to mass of the unit cell by volume of the unit cell, that is equal to Z into M by A cube into Na, where Z is equal to number of atoms per unit cell and M is equal to molar mass of the solid, and A is called edge length in angstroms, and we have to convert them into centimeters or nanometers, and N of A is equal to Avogadro number, that is 6.023 10 to the power of 23. Here A will be given in edge length. So edge length they will give in angstroms, and 1 angstrom is equal to 10 to the power of minus 8 centimeters. 1 angstrom is equal to 10 to the power of minus 8 centimeters. So we have to convert them in either meters or centimeters. So usually we'll convert them in 10 centimeters. So density becomes grams per centimeter cube. Z is here important. Z is equal to number of atoms per unit cell. Now, next, we'll see how the questions will be based on solids density of unit cell. And before that, I want to give you one important table. You can see the table clearly. Number of atoms per unit cell. Number of atoms per unit cell. First one, we know we have, that is indicated by letter Z. For Z for simple cubic, Z for simple cubic is equal to 1. So how we got 1 here? Because for simple cubic, the atoms are occupying all the corners. So 8 corners, and at each corner 1/8 of atom is contributed. So for Z for simple cubic, that is number of atoms per simple cubic, number of atoms per unit cell for simple cubic structure will be equal to 1. Similarly, Z for BCC is equal to Z for BCC is equal to 2. So one is at the center and the other will be at the corner. So what is a BCC unit cell? A unit cell in which the atoms or the ions or molecules occupy all the corners, and one will be at the center. So corners 8 into 1/8 and one will be at the center, that is 1. So total it is 2. This already we have discussed in the previous class. Just again referring it. Next, Z of FCC, that is face centered unit cell, is equal to 4. Because in a face-centered unit cell, the atoms will be occupying all the corners and also at the faces of each, all the 6 faces of the cube. So hence the formula of number of atoms per unit cell for Z is equal to 4 for FCC crystal. So next, coming to second point in this, before solving the problems related to density of crystal, I want to explain you all these things. So first you should know all these things. So number of atoms per unit cell for simple cubic is 1, BCC is equal to 2, and FCC is equal to 4. Now, relation between radius and edge length of a unit cell. Radius and edge length of a unit cell. Radius and edge length of a unit cell. So first one, for simple cubic, R is equal to A by 2. For BCC, second one, for BCC, R is equal to 3 by 4A. And for FCC, third one, FCC, Here I'm writing for FCC, R is equal to A by 2. So this is the relation between radius and edge length of a unit cell. Very, very important for numerical solving. So this table and these 2 points are very, very important for solving questions based on density of crystal. So here the relation between radius and edge length of a unit cell is equal to R is equal to A by 2 for simple cubic. In case of simple cubic, R is equal to A by 2. For BCC, R is equal to root 3 by 4A, and for FCC, R is equal to A by 2. Now we'll see question problems related to density of crystal and radius ratio and so on. So the problems related to density of crystal. So all of you note down this table is very, very important. So for solving problems, both these points are very important. So you please note it down in your classwork. So that's why I'm keeping it for more time. So please note it down in your classwork and then you apply these formulas in the numericals. So now we'll start the numericals. You see question number 1, model number 1 now. How we will get the questions based on this concept, density and radius. Question number 1. The edge length of NaCl unit cell is dash if the radius of sodium ion radius of sodium ion is 97 picometers 97 picometers and that of radius of chlorine ion is radius of chlorine ion is 181 picometers. Is the question. I'm giving the options also. Option 1, first option A, that is 556 picometers. Option B, 278 picometers. Option C, 139 picometers. And option 4, 120 picometers. So now I'm writing the solution for this. Since here, I'll repeat the question again. The edge length of the unit cell, the edge length of NaCl unit cell is dash if the radius of sodium ion is 97 picometers and that of radius of chlorine ion is 181 picometers. Now, already we know NaCl undergoes BCC lattice. NaCl undergoes BCC lattice, and where sodium ions and chlorine ions are at alternate positions. So, edge length is equal to, I'm writing the solution now. So, edge length is equal to, so here in NaCl lattice, it is undergoing what type of lattice? BCC. So, in NaCl BCC lattice, sodium ions and chlorine ions are at alternate positions. Since in the yesterday's class we discussed where the sodium ions and chlorine ions are present, are at alternate positions. Hence, edge length is equal to, hence edge length is equal to 2 into radius of sodium ion plus 2 into radius of chlorine ion. So if I apply this formula, straight away you'll get the answer. So 2 into radius of sodium ion, that is 2 into 97 plus 2 into 181, which comes around 56 picometers. That is first option. Option 1. So in this way, you'll get the question. Simple question. In sodium chloride lattice, already we know it is undergoing BCC lattice, and for BCC lattice, edge length is equal to 2 into radius of sodium ion plus 2 into radius of chlorine ion. So finally you'll get the answer 556 picometers. Next, second question number 2, model number 2. If the edge length of NaH that is sodium hydride unit cell is 488 picometers, what is the length of NaH bonds, that is sodium and hydrogen bonds? Na single bond H, sodium and hydrogen bonds. I'm writing it again clearly. What is the length of NaH bonds? Yes, sodium and hydrogen bonds. If it crystallizes as FCC structure, that is face-centered cubic structure. So in FCC structure also we have, in FCC structure solution I'm writing, options we are writing here first. So first we'll see the options. A is equal to 488 picometers. B is equal to 122 picometers. C is equal to 244 picometers. And D is equal to 976 picometers. So here I'm doing the solution here. So FCC structure also, in FCC structure, that is face-centered cubic lattice, 2 into, in FCC lattice, 2 into radius of sodium ions plus radius of H minus ions, because in NaH, Na plus and H minus is equal to 488 picometers. It is given already. And so the length of NaH bond, so radius of Na plus radius of H minus is equal to, that is length of 488 by 2, which is equal to 244 picometers. And this represents length of NaH bonds. Length of NaH bonds. So answer is third option, that is C. So this is a second model, which is very, very simple. Again, I'm repeating the question. If the edge length of sodium hydride unit cell is 488 picometers, what is the length of sodium hydrogen bonds if it crystallizes as FCC structure? For FCC structure, 2 into radius of cation plus radius of anion is equal to 488 edge length. So R Na plus R H minus is equal to 488 by 2, which is equal to 244 picometers. I hope it is clear. Now question number 3. Model number 3 we are discussing now. Model number 3. These type of questions are very important. So question number 3. A metal crystallizes in a simple cubic unit cell. A metal crystallizes. These questions you also note down and do practice in your classwork when you are listening this video. A metal crystallizes in a simple cubic unit cell of edge length 6.22 angstroms if 6.22 angstroms. Calculate the radius of metal atom is, the radius of metal atom is, option 1, 1.55 angstroms, option B, 3.11 angstroms, Option C, 6.22 angstroms. Option D, 2.45 angstroms. Now, how to solve this type of question? Very simple. Solution I'm writing here. So first repeating the question again. A metal crystallizes in a simple cubic unit cell of edge length 6.22 angstroms. They have given the edge length. Now they are asking us to find radius of ion metal atom. So for simple cubic, as we already know, R is equal to A by 2. For simple cubic, R is equal to A by 2. So implies R is equal to A is given 6.22 because edge length is represented by letter A and by 2. So we'll get the answer 3.11. 6.22 by 2. R is equal to 6.22 by 2 equal to 3.11. R is equal to 3.11 angstroms. So a very simple question. So you'll get all the questions like this only. They'll not give much calculations for NEET level. JEE means they'll give simple calculations. So answer is B. So option B. Next question. Question number 4. Question number 4. Copper crystallizes in FCC lattice with edge length 3.63 angstroms. The radius of copper atom is the radius of copper atom is. So in the previous question, they are given about simple cubic. Now they are giving a metal in place of metal. They are given copper. Copper crystallizes in FCC lattice with edge length 3.63 angstroms. So the radius of copper atom is option A 0.6 angstroms, option B 2.9, and option C 1.28 angstroms, and option 4 that is 5.7 angstroms. Option D. So now we'll see the solution. So already we know first FCC. For FCC, radius is equal to A by 2, 2. The relation between radius and edge length is R is equal to A by 2, 2. So implies R is equal to 3.63 angstroms divided by 2 and root 2. And root 2 value is already, that is 1.414. So by substituting and calculating, we got the answer 1.28 angstroms. So answer is C option. So they will give copper crystallized in FCC lattice with edge length 3.63 angstroms. The radius of copper atom is. Similarly, sometimes they will not give even FCC lattice also. They will give copper crystallizes having edge length 3.63 angstroms. So you should know that copper crystallizes in FCC lattice. So some of the examples of BCC, FCC, and simple cubic lattices you have to remember compulsory, so that to solve this type of questions. And radius of copper atom they are asking us to find. Simple it is. For FCC, R is equal to A by 2. These formulas we have derived. So A value is given 3.63 angstroms, and root 2 value already so by substituting that values you'll get after calculation 1.28 angstroms. So this is model number 4. Next, model number 5. Silver crystallizes here. I'm writing the question. Silver, when I'm dictating and when I'm writing on the board, you also please note down in your classwork. Silver crystallizes in a FCC lattice and has a density of 5 10.6 grams per centimeter cube. 10.6 grams per centimeter cube. What is the length of an edge of the unit cell? What is the length of the edge of the unit cell? Or simply you can say edge length. Edge of the unit cell. So here they have given density and they have given the hint FCC lattice. So density of crystal, usually you may not get density of crystal problems because of huge calculation, but for simple calculations they'll give definitely. So like this here also they have given density and they are asking us to find edge length of the unit cell, and they have given the options 0. First option 0.407 nanometer. Nanometer they are given, that is very important here. And second option 0.2035 nanometers. Third option 0.101 nanometers. And fourth option 4.07 nanometers. Now coming to solution of this. So before going to solution, already you know for density of unit cell. So density is equal to rho is equal to Z into M by A cube into Na. So here we know Z is equal to 4 because this is FCC lattice. Z is equal to 4. Molar mass of silver is 108, and A we have to find because edge length. N of A is Avogadro number, and rho is also given 10.6 grams per centimeter cube. Implies A cube is equal to Z into M by rho into N of A. By substituting these values, 4 into 108 by 10.6 into Avogadro number, that is 6.023 10 to the power of 23. So here 4 comes because of FCC, number of atoms per unit cell, Z is equal to 4, and M molar mass of silver is 108, and below density is given, that is rho is given, that is 10.6, and N of A already we know it is Avogadro number, so it is 6.023 10 to the power of 23. After calculating, you will get the value of A cube, and A is equal to cube root of A. A is equal to what? Cube root of A. So after solving this, cube root of this, you will get the answer. A is equal to 0.407 nanometers. You have to calculate this in your notes. So this is the answer. So option is first option. And here one more important point. Here density is given 10 grams per centimeter cube. Whatever cube root of A you will get, that A will be given in centimeters. So that centimeters you have to convert them into nanometers. So that centimeters means angstroms you will get. And you know 10 angstroms is equal to 1 nanometer. 10 angstroms is equal to 1 nanometer. So from this cube root of this, whatever the value you'll get the value in angstroms, and that angstroms you have to change into nanometers. And for this question, 1 nanometer is equal to 10 angstroms. So since the answer options are given in nanometers, definitely you have to change the given angstroms into nanometers. After finding A value by using the cube root of this expression, you will get A value in terms of angstroms. For that, you have to change them into nanometers. And for that, the conversion is 1 nanometer is equal to 10 angstroms. So after substituting this, you will get the answer 0.407 nanometers. Okay. Next. So these are the important models for finding density of crystal and finding radius or edge length, etc., etc. Next, I'm going to teach you one more important concept, that is called writing formula of a compound. Writing formula of a compound. Writing formula of compound for ionic crystals. For ionic crystals. This is very, very important concept. So definitely they'll ask in the exam. Writing formula of the compound for ionic crystals, very, very important. So before going to this, simply I'll tell you how to write formula of compounds. How to write formula of compounds. Generally they'll give A occupies corners, B occupies face centers, C occupies edge length, etc. etc. So in this case, first the important conversions I am writing here, just note down. Just note down, all of you. Yes. See here. First important point for writing compound formula of compound. If a substance is at corner, it is 8 into 1 by 8. Because it had 8 corners, it has 8 into 1 by 8. So if a substance occupies all the corners, it is equal to 1. Is equal to 1. Second point. If a substance are occupying all the face centers. So in a cube we have 6 face centers, that is 6 into 1 by 2. So it is 3. 6 into 1 by 2, it is 3. Suppose if a substance is present at body diagonal. So we have body edges on body diagonal, body edges. So we have 12 edges, 12 body edges, and at each edge, 1 by 4th of atom is center of each edge, body center, body edges. So 12 into 1 by 4, it is equal to 3. So these are the main things which you are going to, and for body center, for BCC, body center at the center, or you can say body center is equal to 1. Simply it is equal to 1. So these are the assumptions which you are going to see. So if an atom is occupying all the corners, we have to take it as 1 because a cube will have 8 corners, and 8 corners, 1 by 8th of atom is contributed, so it is equal to 1. Similarly, if an atom is occupying all the face centers, so a cube has 6 face centers, and at each face center 1 by 2 of atom is contributed, so 6 into 1 by 2, it is equal to 3. Similarly, if an atom occupies only center edges, that is body center edges, it is equal to 12 into 1 by, because we have 12 body centers, so 12 into 1 by 4. Body center edges, center of the edge, it is 12 into 1 by 4, it is equal to 3. Similarly, if an atom is occupying at the center, it should be considered as 1. So these numbers, why it is important, I'll tell you. Now, we'll see questions based on writing formula of a compound. Very, very important. Now, question number 1. Question number 1. Writing it on the board. Just see. Please note down these questions. Very, very important. A body-centered cubic solid. A body-centered cubic solid is made up of 2 elements. A body-centered cubic solid is made up of 2 elements. TWO 2 elements. A and B. A atoms occupy. A atoms occupy. A atoms occupy corners of the cube. 2 corners of the cube. See, they are giving only 2 corners of the cube. And the remaining positions are occupied by the atoms of B. Remaining positions are occupied by the atoms of B. What is the formula of the compound? What is the formula of the compound? So these type of questions are most important in all the types of competitive exams. By saying this, so option 1, A4B7. Option 2, A7B4. Option 3, AB7. And option 4, it is A7B. Now, how to solve this type of questions? Just see here. They have clearly mentioned a body-centered cubic solid. Body-centered cubic solid is made up of two elements A and B. Here, body-centered means, what is a body-centered unit cell consisting of? A body-centered unit cell consisting of atoms occupy all the corners and also one is at the center. But here A and B is given. A atoms occupy only two corners of the cube. So total out of 8 corners, A is occupying only 2 corners and remaining portion, that is 6 corners and one at the center, that is occupying by B. So by this you can write the answer. A is equal to, since A is occupying only 2 corners, A is equal to 2 into 1 by 8. That is equal to 1 by 4. And B is equal to 6 into 1 by 8. Because remaining 6 corners plus 1 at the center. Plus 1 at the center. So that becomes 7 by 4. 3 by 4 plus 1, which is equal to 7 by 4. Now, A is 7 by 4. Sorry, A is equal to 1 by 4. And B is equal to 7 by 4. Since we do not have fractions in a solid, so multiplying, we have to multiply with a suitable number. So multiplying by 4 for both sides. So we'll get A is equal to 1 and B is equal to 7. So answer is AB7. So option C. AB7, option C. So in this way you have to solve the questions. Very, very important, this model. Again, once again, I'll explain all the solution. A body-centered cubic solid is made up of two elements A and B, in which A atoms occupy two corners of the cube. So they are telling us about BCC lattice, and in BCC lattice, simply we can say atoms will occupy only corners and at the center, all the 8 corners and at the center. And in this case, which atom will occupy corner, which atom will occupy center also they have given. A atoms occupy 2 corners only, but remaining positions are occupied by atoms of B. It means B is occupying 6 corners along with 1 center. So A is equal to 2 corners, that is 2 into 1 by 8, which is equal to 1 by 4. And B is equal to 6 corners plus 1, that is 6 into 1 by 8, because at each corner 1 by 8 of atom is contributed. So B is occupying 6 corners, 6 into 1 by 8 plus 1. So it is coming out as 1 by 4. And by multiplying with suitable number, we get A is equal to 1, B is equal to 7. And the formula of the compound is AB7. Now question number 2. Model number 2 in this formula of compound, question number 2. A solid has a structure in which W atoms, W is called tungsten, W, capital W, W atoms are located at the corners of the cube, are located at the corners of the cube. Oxygen atoms, that is O atoms, oxygen atoms are at the center of the edges, and sodium atom at the center of the cube. The formula of the compound is, is how much? So option 1, first option, NaWO2, sodium, tungsten, oxygen 2. Second option, Na2WO3, Na2WO3. Third option NaWO3. Fourth option NaWO4. So this is the question. Very important model. A solid has a structure in which tungsten atoms are located at the corners of the cube, oxygen atoms are at the center of the edges, and sodium atom at the center of the cube. So they have clearly mentioned three atoms constituting one solid. And what are those three atoms? That is sodium, tungsten W, and oxygen O. So now, since tungsten atoms are at the corners of the cube, definitely W is equal to 8 into 1 by 8, which is equal to 1, because it is occupying only corners. So tungsten W is equal to 8 into 1 by 8 into 1. 8 into 1 by 8, which is equal to 1. And oxygen atoms are at the center of the edges. And already we know we have 12 edge centers. And at each edge center, 1 by 4th of atom is contributed. We have 12 edge centers in a cube. And at each edge center, 1 by 4th of atom are contributed. So 2 by 12 into 1 by 4, it is 3. Similarly for sodium, since sodium is simply divided, they have given sodium atom is at the center of the cube. Center of the cube is only 1. So the answer is NaWO3. NaWO3, because sodium is 1, oxygen is 3, and tungsten is 1. So option is C. So in this way, you have to solve the question. I hope it is clear. Very important model. So a solid has a structure in which tungsten atoms are located at the corners. Since tungsten atoms are located at the corners, so it is occupying all the 8 corners. So 8 into 1 by 8, which is equal to 1. And oxygen atoms are at the center of the edges. We have 12 edge centers. Note this. We have 12 edge centers in a cube. So out of at each edge center, 1 by 4th of atom, we have 6 face centers, 12 edge centers. So here they have given edge centers. So 12 into 1 by 4, which is equal to 3. So sodium is equal to, and sodium, so oxygen atoms will be 3. And sodium atom is at the center of the cube. Since sodium is at the center of the cube, it is only 1. So sodium is 1. So answer is NaWO3. Next question. A compound formed by, when I'm dictating and writing, you please also write down. A compound formed by elements X and Y crystallizes in a cubic structure, crystallizes in a cubic structure in which X atoms are at the corners of the cube, in which X atoms are at the corners of the cube, and Y atoms are occupying all the face centers, are at the face centers. Then the formula of the compound is, option 1, X3Y, option 2, XY, option 3, XY2, and option 4, XY3. That is option D. So 1, 2, 3, 4. There 1, option 1, 2, 3, and 4. Now, if you see the solution for this, simple, it is directly given. A compound formed by elements X and Y crystallized in cubic structure in which X atoms are the corners of the cube. Simply, X is equal to 8 into 1 by 8. And Y atoms are occupying at the face center. So Y is equal to 6 into 1 by 2, that is equal to 3. So answer is XY3. Fourth option. Next question. Now, these are the easiest questions. Next, we'll go a little bit tougher questions. That is, next question. A compound is formed by, this is a simple question only. A compound is formed by elements A and B. Elements A and B, in which elements A and B, in which A atoms occupy all the corners of the cube. All the corners of the cube, and B atoms occupy alternate phase centers. What is the form of the compound? Here I'm not giving any options. Directly I'm writing the solution. What is the formula of the compound? So here, a compound is formed by elements. Again, I'm repeating the question. I hope you have noted down. A compound is formed by elements A, B, in which A atoms occupy all the corners of the cube and B atoms occupy alternate phase centers. What is the formula of the compound? So here they mentioned A is clear, that is A is equal to, solution I'm writing here, since A is occupying all the corners, A is equal to 8 into, at each corner 1/8 of atom is present, so A is equal to 1. Next, B is occupying alternate phase centers. Since we have 6 phase centers and B is occupying only 3 because it is occupying only alternate phase centers. So alternate phase centers means B is equal to 3 into 1/2 because it is occupying only 3 phase centers. 3 into 1/2. At each phase center, 1/2 atom of it is 1/2 atom is contributed. So B is equal to 3/2. So A is equal to 1. B is equal to 3/2. Multiplying by 2 for both, we got A is equal to 2, B is equal to 6, B is equal to 3. So answer is A to B3. Answer is A to B3. This is little bit different model. Next, question number 5. We have so many models. Sometimes they'll give diagram also, but here I'm not doing all those things. That also we have discussed. We'll discuss in next class. In a compound, atoms of element Y. In a compound, this question is a little bit typical. In a compound, atoms of element Y forms CCP. Atoms of element Y forms CCP. When I'm dictating, I'm also writing on the board. So you also please write it in your classwork. That is, and those of element X. Those of element X occupying occupies 2/3 of tetrahedral voids. 2/3 of tetrahedral voids. What is the formula of the compound? What is the formula of the compound? For this also I'm not giving options. So straight away we'll try to solve this question. Here in this question, in a compound, atoms of element Y forms CC lattice, and those of element X occupies two-thirds of tetrahedral voids. Two-thirds of tetrahedral voids. So, what is the formula of the compound? Here, this is a different question. Y is clear, it is given CC lattice. Since Y is occupying CC lattice, Y is equal to 4. Because CC lattice represents FCC, means it means Y is equal to 4 because Y is occupying CCP lattice. CCP lattice means FCC, in which Y atoms are present at the corners, also at the all the 6 face centers. So it is CCP means FCC, already we discussed. So straight away Y is equal to 4 wheel, right? Whereas X here, X occupies two-thirds of tetrahedral voids. For the same lattice, in the tetrahedral voids, X is present, and that also only two-thirds of tetrahedral voids is present. So for this case, X is equal to 2/3 of tetrahedral void, two-thirds of tetrahedral void. And for CCP, number of tetrahedral voids is equal to, for CCP, number of tetrahedral voids is equal to 2 into n, where n is equal to 4, because for FCC lattice or CCP lattice, number of atoms per unit cell is equal to 4. So for number of tetrahedral voids is equal to 2 into 4, 8. And out of this, X is occupying only two-thirds. So X is equal to 2/3 into 8. So which is equal to 16/3. Now by this we got Y is equal to 4 and X is equal to 16/3. So multiplying by 3 for both sides, for both X and Y, we got Y is equal to 12 and X is equal to 16. By taking common, X is equal to 4, because 4 divides in 16 4 times, and because 12 and 16 still we can divide them. So X is equal to 4, Y is equal to 3. So answer is X4 Y3. X4 Y3. This is the answer. Very, very important model. So they are asking tetrahedral voids. Tetrahedral voids means for any lattice, number of tetrahedral voids will be 2 into n. For any lattice, very, very important point, note down. For any lattice, number of tetrahedral voids is equal to 2 into 1. So in this CCP lattice, 2 into n is tetrahedral voids. N is equal to 4, because n is nothing but z also. We can represent n of z. So number of atoms per unit cell z is equal to 4. And for any lattice, number of octahedral voids is equal to n, and for any lattice, number of tetrahedral voids is equal to 2n. Very, very important. I'm writing it again, the statement. For any lattice, number of octahedral voids, O dot V, is equal to n, whereas number of tetrahedral voids is equal to 2 into n. This point is very, very important. So n is nothing but here z, because some books they'll give n as z or n, both are same. So that's why for your understanding, number of octahedral voids is equal to n in any lattice. For example, if you take simple cubic, number of octahedral voids will be equal to 1. And for body center, number of octahedral voids is equal to 2. And for face center, number of octahedral voids is equal to 4. Similarly, number of tetrahedral voids will be, for simple cubic, it is 2 into n, that is 2 into 1. For body center, 2 into 2, that is 4. And for face center, 2 into 4, that is 8. So in this way, you have to remember, these questions are very, very important. Next, last model we'll do. That is also typical problem. It has come for IIT, JEE Mains. That is IIT advanced level also it is there. So next question, important model. In a face-centered cubic arrangement, little bit higher difficulty model. In a face-centered cubic arrangement, the same question has come for IIT. In a face-centered cubic arrangement of A and B atoms, cubic arrangement of A and B atoms, in which in which A atoms occupy corners of the unit cell. A atoms occupy corners of the unit cell, and B atom occupies B atom occupies phase centers, comma. If one of the atom of A is missing, if one atom of A is missing from one corner of the unit cell, missing from one corner of the unit cell, one corner of the unit cell, the simplest formula of the compound is the simplest formula of the compound is the simplest formula of the compound is. So this is model number 6, very, very important. In a face-centered cubic arrangement of atoms A and B, in which A atoms occupy corners of the unit cell and B atoms occupy face centers. Still here it is very clear. And we can say A is 1, B is 3. But one of the atom of A is missing from one corner of the unit cell, then the simplest form of the compound is. So in this case, first, since A is occupying, A should be present in 8 corners, but one of the A is missing from corner. So solution I'm writing here, solution. So A is only 7 corners we have to take because A is present only at 7 corners because one atom of A is missing from the one corner of the unit cell. So A is equal to 7 into 1 by 8. 7 into 1 by 8, which is equal to 7 by 8. And already we know B is equal to, B is occupying all the face centers. So B is equal to 6 into 1 by 2, that is 3. Now A is 7 by 8 and B is 3. So we have to multiply with suitable number. So that is 7 by 8 into 8 to get number because A is in fraction. So A is equal to 7, B is equal to 24. So answer is A7, B24. So in this way also you'll get the question. This is question number 6 based on writing formula of a compound. So all these questions are most important. So in this session, we have discussed successfully all the questions related to finding density of crystal as well as writing formula of a compound, because this session is most important. That's why I have selected a few questions for your understanding and I have discussed all these few questions in case of both the topics. So that's why very, very important topic, and this session, please understand it. And when I'm dictating and I'm writing on the displaying board, so you also please write down in your classwork and practice these questions and solve more and more questions from the objective materials. Easily you can understand this concept. So density of crystal and writing formula of a compound is most important. And in next session, we'll discuss the problems related to all the topics in this chapter. So in the next session, we'll do the questions based on exercise based on solid state. I hope you understood clearly, and I'm ending this session. Thank you, one and all. I'm ending this session.